Back level 1 NCEA physicists looking at energy bar charts today as an extension or a continuation of the achievement standard with looking at physical systems through the idea of an energy lens. So energy bar charts basically illustrate clearly the law of the conservation of energy. They're very useful and intuitive as tools, and they're also known as LOL charts, and we'll soon find out why. The first thing is, well, why use energy bar charts? So how would you say a wind turbine works? So you'd say, well, the kinetic energy from the wind then starts to move the turbine, so the turbine gains kinetic energy, and then that creates electrical energy. But does this actually help you understand the processes actually going on with the wind turbine? Well, energy really doesn't explain physical processes. We use energy as a tool in physics using the idea of conservation of energy. And the idea, of course, is that the total amount of energy in a closed system stays the same in terms of energy transformation. So energy is basically being transformed into different forms. And energy bar charts, or LOL charts as it's also known, help you visualize this. So in terms of creating energy bar charts, let's look at the example we already looked at in the previous lesson, a cart rolling down a ramp. So the first question we're going to ask is, well, what is the system? Okay, well, the system is that cart. The initial state, the cart is going to be on top of the ramp, and then at the end, the final state, when you take that snapshot, the cart's going to be at the bottom of the ramp. So what's changed? Well, the cart has lost height, or gravitational potential energy. Remember, EP equals mgh. And it's also gained speed. So therefore, EK equals half mv squared. So the kinetic energy is increased. So as you can see on the right, initially, you can start to draw the empty bar charts. And you can see why it's called an LOL chart. Okay, so on the left, we have the initial state, the first L. In the middle, we have the system that we're working in, the O, and then the final state is going to be the second L. And then we can start filling it in. And you can see that the amount of energy in joules of the gravitational potential energy initially equals the amount of kinetic energy after the process has occurred of it falling down and losing that height. And the system, which goes in the O, is going to be the cart itself. And that's an LOL. So it shows you the final initial states and also the system. However, really, is that what is happening? So you'll also notice that the number of bars in the initial state equals the number of bars in the final state. So what's that saying is that the kinetic energy equals the gravitational potential energy. So the kinetic energy in the final state equals the gravitational potential energy in the initial state. Conservation of energy in a closed system. But then think about the friction of the axles. How will this change the cart? Well, you'll see from the bottom diagram on the right that the kinetic energy decreases and the thermal energy from the friction increases, but still the energy at the start, the initial state, equals the sum of the kinetic energy plus the thermal energy in the final state. The number of bars, as it were, is the same. We start with 5 bars, 6 bars, 1, 2, 3, 4, 5 bars, and we end up with 5 bars at the end. 3 bars for kinetic, because it's going to slow down as well, the velocity, because of the friction, and you get that heat energy as well, and it's going to be 2 bars. But the key point is that energy is conserved. So another way of looking at it is also through energy transfers, which we touched on briefly as well. So now the toy cart is being pushed back up by your hand at the top of the ramp. So the system again is the cart. The initial state now is the bottom of the ramp, and the final state is now back at the top of the ramp. So now what's changed? Well, the height is now increased. You've now got more gravitational potential energy, but there's no kinetic energy involved in that process. The chart shows that initially, the initial state is there's no gravitational potential energy, there is no kinetic energy, and what's happened is you've done work on the system, the cart, and you can see that on the arrow on the right. And you'll see that the amount of work is 1, 2, 3, 4, 5 units, and the amount of gravitational potential energy that is now gained is also 5 units. So energy is again conserved. So work has been done on the cart, so it has to be added to that system. And that, in a nutshell, is, in a simple sense, how we can create energy bar charts or LOL charts.